What if we had a really, really cool telescope? What else could we see? Not quite. Not yet. Pulsars. Really crazy galaxy clusters, right? Planets themselves, actually directly imaging other planets. This is kind of what we're able to do through the use of the visual spectrum. See stuff directly and use telescopes to see stuff that's really, really, really far away. And most of what has been the scope of human observation of our universe, including our galaxy, our solar system, etc., has used the visual spectrum. So, what else is out there that we may not be seeing? In order to answer that question, we're going to talk about some terminology. We'll go through some confusing things that we see through observational evidence and what those things could possibly mean. And then we'll talk about how we might be able to explore those topics more intelligently. Once we've done that, we'll talk about how we were able to discover some new technologies. Scientists at a couple of labs, one in Washington State and one in Louisiana, and the implications of that find. Questions before we get started? All right, we'll have a question for you. What is gravity? Simple answers are okay. Henry, what is gravity?
What keeps you down?
What keeps you down? Okay, that's a very pessimistic answer. What else? Yes?
It's like an attractive force between everything.
Okay, good. Good. It's an attractive force. It helps bring things together. That's a very critical quality of it. Anything else? Yes?
It can warp space-time.
Yeah, and that's its critical feature here, is that it warps space-time around massive objects. Okay, so it's a warping or curving of space-time around really big things. So in this image, you can see the Earth and this web of space-time that's being molded around it. We'll talk about what that means a little bit more later. Second question, what is a black hole? This is also a really cool picture.
What is a black hole?
Yeah, what are black holes? Natalie?
Floating in space so dense with so much mass that it's sort of becomes swallowed by gravity and it starts pulling things in its incredibly strong gravity, and also time can escape it and things once there's the event horizon.
Mm-hmm.
After you pass the event horizon, there's no way to
Middle schoolers are the best. Scientifically proven. Yeah, so black holes have a couple of really critical qualities. One is that they're supremely, supremely dense objects in our universe. They're so dense, in fact, that light is incapable of escaping their gravitational attractive force. So, let's think about an example of what that would mean in real life. For the purposes of the paper we're going to talk about today, we'll be exploring a black hole with 62 solar masses, which is to say it weighs 62 times the mass of the sun. This is the sun. It's very big. This is the Earth. For those of you who can see that tiny dot, the sun is much bigger than the Earth. In the case of the black hole we'll be talking about today, it's worth 62 of these in terms of mass, squeezed into the distance between New York and Boston. It's a lot of stuff in a very, very tiny space. Such a tiny space that when light enters its event horizon, it actually can't escape. Why is that so important for the purposes of our observational techniques?
Can't see it.
Can't see it. That's right. So, the last piece of terminology is a gravitational wave. And that's a little bit complex. So let's start with a simpler definition. What is a wave? Natalie, I'm not going to call on you again. I'm going to make these upper schoolers carry their weight. What's a wave? You're wearing a Patagonia shirt. You're like a surfer, bro. You know what a wave is. What's a wave?
Something you find in the ocean.
Yeah, it's like tubular, right? Yeah. Okay. So a wave is energy or some force being transferred through a medium. In the case of ocean waves, that's energy through gravitational force, through things moving through the ocean, forcing water to move through the transfer of energy. Okay, sound waves are the same thing. Energy transferred through air. In the case of gravitational waves, these are waves that are transferring through space-time itself. So, if gravity and its critical feature is the curvature of space-time, these ripples are rippling through space-time across the universe. And they're caused by very, very powerful movements in the universe. So, as we see here, this is the merger of two black holes, which is what we'll be talking about today, which is a very violent action, which is important because gravity is a very weak force. So as we think about whether we'll be able to see light, see different things in the universe, we would have to have very, very sensitive instruments to be able to see or sense gravitational waves. Questions on any of the terminology so far? Parth?
How can the black holes trap light if light doesn't have mass and gravity is usually a mass thing?
Good question. Because they are, I'm not sure exactly how to answer that.
Well, it's probably because
Sure,
of the
exactly.
duality thing. It's like you get particle or
I think both forms don't have mass.
Right, right, right. In as much as it is energy, it can be captured within that gravitational pull, I think. I'm going to go with that. Good question, then. Okay. So, let's get started. There are a couple, yes?
I have a question.
Yeah, go ahead.
What is space-time?
Space-time. So this is the fabric of our cosmos. Okay, so space-time, that's a very good question. That's probably something I should have defined. Space-time is everything. As you look out in space, it's a void, right? But actually, there's lots and lots of stuff in it. Okay, and that kind of matter that makes up everything in the universe. So us, gravitational waves would pass through us. They would pass through our planet. They just happen to be very weak, so we wouldn't feel it.
Okay.
Yeah. Okay, so most of the universe is missing. When we looked at that night sky, what are some things that we saw? Stars, galaxies, planets, right? When we look at the universe, one of the troubling things that scientists have discovered is that all of the evidence that we have indicates that all of the stuff we see represents just 5% of the universe. Just 5%. So what is everything else? Well, there are two things. One is dark matter, and the other is dark energy. We're going to talk a little bit about why we think those things exist, and then we're going to talk about what we can find out about them. So dark matter is insinuated by a couple of theories. One is observational evidence that at the center of every galaxy is a supermassive black hole. Okay, the black hole we were talking about today is about 60 solar masses. A supermassive black hole could be millions or billions of solar masses. Really, really big ones. And so a galaxy is actually a cluster of stars moving around this supermassive black hole. Questions on that? Okay, so what happens, one would expect, is that things closer to the supermassive black hole, stars for example, would move really quickly, and things on the farther reaches of that galaxy would move much slower. However, based on observation, what's bizarre is that all of the stars move at a uniform speed around that supermassive black hole, which makes no sense based on our understanding of gravity. So, scientists believe that there is a lot more matter than we're seeing in those galaxies. And that matter is dark matter. That's basically what they call it. Dark meaning that we don't necessarily understand it. And what's crazy is that the calculations insinuate that there should be 5 times as much matter than we're currently seeing. Okay, so that's 25% of the matter in our galaxy and in the universe. So there are a couple theories as to what these things might be. One is primordial black holes. This would be a black hole that formed at the very dawn of our universe in the Big Bang. We haven't been able to find much evidence of that yet. Another leading theory is WIMPs, not the kids you beat up and stuff into lockers, but rather weakly interacting massive particles. Okay? What that basically means is it's a really big, massive particle, which is to say it has a lot of gravitational attraction. However, it's non-interactive, meaning it wouldn't interact with photons or electrons or other things in the universe around it. So we wouldn't see it, but it would be felt through its gravitation. The next big question is dark energy. And dark energy is another thing that's insinuated based on what we are seeing about the universe. So scientists know now that the universe was created in the Big Bang, which is a lot of matter expanding, creating a dynamic of an expanding universe. Now, as we know, gravity is an attractive force. So the combined weight of everything in the universe should be gradually slowing down that acceleration, that expansion. But what scientists were able to find out when they went to measure that rate of deceleration is that by looking at stars and measuring how quickly they're moving away from us, that expansion is actually accelerating, which based on our theories of gravity doesn't really make sense. Which insinuates that there's some force, some energetic, dark energy force, driving the expansion of the universe, the continued accelerated expansion of the universe, against what we would expect. Questions on any of those things so far? Yeah, Tommy.
You said we can only see like 5% of what's in the universe?
Yeah.
I thought the universe was infinite.
It is not infinite. It is not infinite. Because the universe was created at a finite point, the Big Bang, it is still expanding. Okay, so there is a finite edge to that universe. We can't see it because it's too far away, but it's called cosmic background radiation. Basically, if you look at the waves that were created at the very dawn of existence, we can insinuate the age of the universe. It's tricky and probably more complicated than I can understand, but that's what Neil deGrasse Tyson told me. In like videos and stuff, not actually because that'd be cool. We have a paper. This is called The Observation of Gravitational Waves from a Binary Black Hole Merger. And we know what gravitational waves are now, but a binary black hole merger. Binary meaning two. So we have two black holes that are merging through circling around each other very, very, very quickly, and then becoming a single black hole. This is going to be particularly important because these gravitational waves result from particularly violent interactions. And the merger of two black holes is amongst the most violent interactions that exist in our universe. So, how scientists detect these things. So in the 70s, scientists came up with a methodology that they thought they could use to detect gravitational waves. And this is a laser interferometer gravitational wave observatory, hereafter known as LIGO. So, what would LIGO actually do? LIGO is essentially a really, really big laser. And that laser is forced through a beam splitter, creating two negative lasers that when recombined cancel each other out. So a good representation of this is this right here. So we got one wave going through A, and because it's a laser that's been split, its negative aspect is going through B, which means when we recombine them, they would cancel each other out entirely, resulting in no signal. However, if there were an invisible gravitational disturbance passing through them, it would disrupt that signal, resulting in something. Okay, so the lasers are going out and coming back in, and if there's something disrupting those lasers, they wouldn't sync up perfectly, resulting in a signal. Now, there are lots of things that could cause that, and lots of things that do cause that. In theory, something like an earthquake could register on that. However, they have a lot of different instruments that try to make them as sensitive as possible, which is to say that they won't sense things that happen on Earth, they'll sense things that happen very, very far away. And moreover, there are two of them, which is to say the one is in Washington State, one's in Louisiana. If there were some local phenomenon in Washington that caused a disturbance, that wouldn't be felt in Louisiana, so they can kind of cross-check each other. Questions? Yeah?
When they were finding this information, how old is the data that they're receiving back from space?
Good question. We'll get there. So, what scientists observed was an increasing oscillation in frequency and power here that was matched very closely between the observatory in Washington and the one in Louisiana. And what scientists did was they took a mathematical construction of what gravitational waves should look like based on Einstein's theories, which is to say they had a mathematical equation modeling out what a gravitational wave would look like. They compared that against their observation and took all of the excess information and plotted it. That's this residual here. Now, if that information looks random, it means that the strength of the correlation between the data they received and the data they calculated based on general relativity is very close. And as we can see, that information is fairly random. As we look at these data points here, they very closely match. with what we would expect based on mathematical theories of gravitational waves. So, what could cause that gravitational wave? Well, scientists can use the frequency of the signal combined with the duration of the signal to try to determine a few things. They can determine how long it took for the two things to merge, how much mass they have, etc. Now, what's critical to understand here is that this is oscillating in greater and greater frequency here because as the black holes get closer to each other, the relativity of their spin around each other, the relative velocity of their spin around each other increases, which is to say the violence of those gravitational waves is becoming stronger as they approach each other. Okay. So, again, based on Einstein's theory, as these massive things approach each other, they create gravitational waves. And this specific event, scientists believe, was caused by two black holes. And there's a couple reasons they think that. One is because if you had two binary neutron stars, for example, which are not black holes, but they're very dense stars, they would actually have merged before they got to the frequency they saw. So because their relative volume to their density is lower than that of a black hole, they would have merged before they got to the frequency they saw, which is to say the velocity they had spinning around each other wouldn't have matched what they observed. So let's talk about what they actually saw. This event is called GW150914, and scientists believe it was caused by the merger of two black holes. Now, these two black holes had solar masses of 36 and 29 times the mass of the sun, and the resulting black hole is 62 solar mass units, which means that there were, what's the math here? 3 times the mass of the sun that was expelled as energy as these two things were merging around each other. And that energy is in the form of a gravitational wave, which means that the amount of energy poured into these gravitational waves is extremely powerful. In fact, if you look at the power of the gravitational wave that was created by the single event, it's more powerful than all of the light in the universe combined. It's very, very powerful. And to answer, is it Katie? Jenny. Oh, Katie was your sister. Oh, that's bad. Sorry. Jenny's question. This occurred at a distance of more than 1 billion light years away, which means how long ago did it happen? Natalie? Billion years ago. A billion years ago, the Earth was a giant snowball, and the only life that existed was single cellular. It's a very, very long time ago. Yeah?
Isn't that only if gravitational waves travel at like light speed?
They do.
They do.
Based on theories, yeah.
Okay.
Yeah, that's right. So, yeah, Buzz Lightyear, because Lightyear, right. Yeah.
How long did this event take?
Good question. I don't know exactly how long it took, but it was very rapid, which is to say that it's not something they were measuring over days, but rather... That's right. Especially as that relative velocity is increasing as they're drawing near to each other, it happened very rapidly. Yeah, right.
So were the scientists able to capture the whole thing from start to finish?
That's right.
Okay.
Yeah.
And, sorry,
No,
how
that's
does
okay.
the laser experiment translate to that graph we saw?
Okay, so the signal that would have resulted from the disruption of these lasers when they're recombined is this signal. So that signal represents the disruption of the lasers from what they should be, which is just canceling each other out. So, based on all of that, we know that this is insinuated through the use of lasers. So how do we know that this wasn't some random event that happened to trigger a mechanism in these lasers? Well, scientists performed a statistical analysis looking at the likelihood that a random event would have caused this same phenomena to occur. So, based on their calculations, the likelihood of that is 5 sigma, which is to say that it's extremely rare that a random chance event would have caused the same exact data they saw. That actually means that given the fact that these machines were operational for like 15 days before they made an observation, scientists would expect that a random event of the power and description that they saw would happen once in every 200,000 years, which is to say that it's probably not a random event. So, what does this mean? Well, we've kind of tapped out a lot of the means that humans have for observing the universe through the light spectrum. That's not to say that we know everything or that we've seen everything. We're still seeing new exoplanets and solar systems and different things every day. But the means that we have of exploring the universe for the visual spectrum have largely been tapped out. So gravitational wave astronomy represents a new way that scientists can find out more information about our universe, which is particularly pertinent given the fact that these pieces of information, like dark energy, dark matter, we can't see those things through the visual spectrum. So scientists are expanding the number of LIGO apparatuses throughout the world. There's one in Germany now, one in Italy, and 2 more that are under construction. The more different apparatuses we have, the more sensitive information we can detect. Now, additionally, the European Space Agency and China are both putting up LIGO apparatuses in space, which is to say that the further away they are, the more accurately they'll be able to try and triangulate the location of signals and gain more sensitive information about them. That's all I got. Any questions before I get out of here? Yeah, go ahead.
So how often do the mergers of black holes occur? If they've caught it in 15 days, is it by chance or do they occur pretty often?
That's what scientists are trying to figure out right now. Did we just get very, very lucky? Or do these things happen much more frequently than we would expect? The answer is probably the latter, but until we have a lot more events, it's hard to say that. Yes?
What are the consequences of the gravitational waves? Like, do they disrupt any neighboring, like, stars or planets or anything?
They can. So for example, one of the ways that scientists are looking at gravitational waves from supermassive black hole mergers, our instruments are not nearly sensitive enough to detect waves at such a low frequency, but what they're actually doing is they're looking at pulsars. Does anyone know what a pulsar is? It's a very rapidly rotating star. So it's like a lighthouse, beaming light out into the universe, and it happens so frequently that we can see it spinning like, however many times per second. So we can use that as a clock. And what we do is scientists measure the rate at which the Earth is rocking back and forth through massive gravitational waves by checking the time and seeing if there's any disruption in the time between those pulsars.
And disruptions would be from
Yeah, it would be from supermassive black holes. So there are other means of detecting gravitational waves, but the LIGO apparatus will detect very violent ones. The huge ones will affect us, but not in any way that would be harmful or anything like that. Other questions? Yeah, go ahead, Sean.
Have the instruments picked up anything since, or is that the only important one that they have?
As far as I'm aware, that's been the only discovery. And it was in 2015, so. Yeah, go ahead.
Do you know much about the jets that come out of black holes and how that might affect the experiment?
I don't. It's a good question because the merger of these black holes resulted in the energy which formed the gravitational waves, right? So understanding, I'm sure there are people who understand far more about that than I do. But yeah, it's a good question because ultimately understanding the fact that energy can be expelled from black holes in the first place, which is kind of incompatible with their whole nature of not letting light escape, is confusing. But yeah. Are we out of time?
Yeah.
Okay. All right. Thank you guys very much. Next week,
Allie, 5.